Welcome to Lecture 2.4a. So the last topic in the chapter, and actually the last topic before we take our unit test, is actually a revisit to the very first thing we ever talked about in limits. Average change and instantaneous change. This was the motivation for the whole reason we came up with the whole idea of a limit in the first place. Before I show you how it's now going to pay off, let's do a quick warm-up example. So find the average change of this cubic function on this interval. I've set up my work as we normally do with word problems, and the first step after I know what information I have to start with and what I'm looking for is to make sure I understand what this means. You should remember from the very beginning, or if you don't, let me remind you, that average change is really talking about the slope. And this is a curved line, so obviously it doesn't have a constant slope. So we're talking about the average slope, which means we're going to need 2 points, and we're just going to calculate the slope between them. This interval is really key. This interval is telling you the first x value and the second x value. Don't accidentally make the mistake of thinking this is an x and a y. This is an interval. We always designate intervals on the x-axis of the function. So this is where we're starting, and this is where we're stopping. And that's actually how you start the work. Since we know we're going to calculate slope, we need to be able to find y2 and y1, and we'll use x1 and x2 to do that. Let's start with the first point. Since we know that for the first point x equals 1, it's actually pretty easy to find the y value. I would recommend that you show your work like this. X equals 1, and then y is going to be the output of this function when I plug in 1. In other words, I'll take 1, plug it in up here, 1 cubed minus 1, well that's just 0. So there's my first point, and it might be easiest to read it if we just write it as a point really quickly. 1 comma 0 is where we're starting. We need a second point to calculate the slope. So second point, here we go. Same idea. I have an x value to start with. That x value is 3. The y value is going to be the output of this function when I plug in 3. That's what f of 3 means. Now to actually figure out what that number is, we just go ahead and do the math. 3 cubed is 27. And 27 minus 3 is 24. So our second point is 3 comma 24. Now the actual answer is going to be the slope. And slope is usually represented with an m, so this will just help my work be clear. But I'm just using the slope formula, y2 minus y1 over x2 minus x1. 24 minus 0 is 24. Divided by 2 is 12. And let's go ahead and write a sentence out really quickly, just because we will be doing word problems. So I would say the function's average change is 12. And you would add units if you had units. We don't have one today. Go ahead and look at the second example. Model your work after mine, and then I'll show you the answers in a second. Great, so here's the work as I would have shown it. It's a pretty simple idea. And now that you're solid with that, let's talk more about calculus. So this whole idea of average change, we came up with this originally because we were talking about speed. We were talking about race cars, actually. We wanted to know how fast this race car was going. And initially, we thought, well, that's easy. Let's just calculate the slope of the distance time graph. But then we realized that actually calculating the slope, just using the beginning point and the end point, doesn't tell us everything about how fast the car is traveling. In fact, what we just did, calculating the average, is an average speed. It's an average rate of change. And what we were really interested in with these race cars was not just how fast they were going on average, but how fast they were going at a particular point. And so then we had this kind of fuzzy idea of using a limit to find the speed at a particular point. Today's lecture is all about these two ideas, and this is where we actually get to do the examples. Before it was just talk. First, let's define two things: secant line and tangent line. A secant line connects 2 points that are on a function. In particular, these 2 points have a slope and an equation that goes through this secant line. A tangent line is a line that touches a curve at exactly 1 point, but doesn't cross. So notice that if we extend the secant line, it would cross the blue function, but the tangent line would not do that, and that's the distinct difference between the two. Also notice that when you have a secant line, you have 2 points, and when you have a tangent line, you only have 1. That's going to turn out to be a problem in just a couple minutes. So in today's lecture, we're going to use an example about fruit flies. Fruit flies are commonly used in medical research or just in biology, partly because they reproduce so quickly. And this graph is an example of the data that a scientist might track if they were doing an experiment with some fruit flies. What do the x and y axis represent? Right, so that was easy. Now thinking about the x and the y axis, if we're measuring how many flies there are on a given day, what would the slope of a graph like this mean? So hopefully you were able to articulate that the slope would represent a number for how the number of flies is changing with respect to time. So what if we actually wanted to know, how are these fruit flies changing? There are 2 different questions we could ask. We could ask, on average, how quickly did the population grow? Or we could ask, on a particular day, how fast were the fruit flies growing that day? And that's going to require 2 different calculations. Let's start with A. So on day 23, I can read this graph, and actually they help us out by telling us a point, and they tell us that there are 150 fruit flies. On day 45, they tell us that there are 340, although we could have just read that off the graph. To calculate the average rate of change, I'm just going to find the slope between those 2 points. So it's y2 minus y1, which is going to be 340 minus 150, over x2 minus x1, so 45 minus 23. 340 minus 150 is 190. 45 minus 23 is 22. And if I grab my calculator and divide those, I get an average rate of change of 8.636. And since we are talking about a real-world problem here, we want to use units. So I'm going to go ahead and approximate, and we'll say the flies population is growing approximately 9, and the units are flies per day. Turning to B, the goal for B was to calculate the population growth on day 23. So if I go back to the graph for a second, obviously we have this 1 point, which is 23, 150. Now, maybe my instinct would be to calculate a slope again. So if I just get the idea of calculating a slope with that point, I would calculate 150 minus 150 over 23 minus 23, because I want just that exact day. Now, obviously, there's something wrong here, because we would get 0 over 0. So it turns out we can't use the slope to find the population just on that day. And in fact, what that means is that there's no way using the slope formula to calculate the slope just at that point. Instead, what we're going to have to do is we're going to have to estimate it. And this picture shows you an idea of how we'll estimate it. Here's the idea. We're going to start by calculating the slope of this secant line. In fact, we already did. It was about 9. And then we're going to calculate another slope. And the next slope is going to be the slope of a secant line that's slightly closer to my original point. And then I'm going to calculate another slope using a point that's even closer. And then as these points approach my original point, the slope of these lines is getting closer and closer and closer to the slope of this black line. And ideally, this black line is the tangent at that point, the instantaneous change. Here's one way to show your work. Since we're going to be calculating a bunch of secant lines, I would maybe set up a table where we can record the interval and the slope of the secant line. In fact, we've already done this for the first interval. The first interval that we looked at was the interval from 23 all the way to 45. And the slope that we found was approximately 8.6. Well, if we wanted to get a more accurate slope, because we know that 8.6 is the slope of this line out here, which isn't really very close to the instant slope, we would pick a new y2 and x2 that was a little bit closer to our original point. So I'm going to pick the point at 40, and I'm going to estimate that the y value here is approximately 330. When I do that, I can calculate a new slope for the interval from 23 to 40. Remember, these are x values. The new slope, we calculate it the same way using the new y value. 330 minus 150 over 40 minus 23. And this value, when we subtract everything out, becomes 180 over 17, which it turns out is approximately 10.6. Now, the next step is to do this again, and we want to pick another interval that's even closer to that original point that we're really interested in. So for example, we could go from 23 to 35. And to calculate the slope, we would go back, look at the graph, here's 35 on the x-axis, go up, estimate the y value, maybe it's 310, and then we would come back and we would use the slope formula again. So 310 minus 150 divided by, this time, 35 minus 23. And we're going to end up with 160 divided by 12, which is approximately 13.3. And we could continue this process. The next interval would be something like 23 to 30, and maybe we could even go as small as 23 to 25 if we were really careful. Well, I'll spare you the rest of the slope calculations because I think you can see how it's going to work. And I'll just let you know that this estimate of the slope is going to be approximately 16.4 and then approximately 16.9. Now, once you've done all these estimates, the actual answer here is supposed to be the slope right at that point. Well, think about what we've learned with limits. As these lines get closer and closer and closer to this point, what's happening to their slopes? The slopes are increasing, and in fact, it looks like they're getting closer and closer to something around 17. We don't know if that's really the slope. That's an estimate. And that's an estimate that's based on these calculations that we've done. It's not a precise number. We'll learn next unit how to precisely calculate this slope. For now, we're just going to rest with that estimate. So we're going to guess that the fly population is growing approximately 17 flies per day on the 23rd day. Use this same idea to think about a different example. And we will come back to this second example in class.